Thanks for taking my talk. Today I'm going to talk about simple vector addition systems of states, whatever simple means. I'll quickly define a VASS soon. This is about joint work with Dmitry Chistokov, Wojciech Czerwiński, Filip Mazowecki, Łukasz Orlikowski, and Karol Wyszyński. They got accepted to Fox. Before I talk about VASS, I thought I should start with a joke, right? And the joke starts with a lovely screenshot that Wojciech took just when we were deciding to submit to Fox. I thought it's kind of unlikely you get a VASS paper into Fox, right? So I thought, how to get a Fox paper. So the first thing you do is you attempt to submit to stock. And that's like 6 months before. It sounds like a good idea. We all said yes. And then you need one co-author that says, oh, we don't have time. I need more time to work on this. And then you go, okay, fine. Like, what if you submit to ICAP instead? That sounds like a good idea. Yeah, everyone agrees. And then you need the co-authors again say, I need more time. It's like, okay, fine. What about if we submit to Fox? Okay, that sounds like a great idea. That'll be fine. Oh no, I need more time. It's really frustrating. But I was only joking the whole time. It's fine. We can submit fast. So yeah, this conversation might not be 100% accurate. Don't worry. Anyway, so I have the pleasure of defining VASS because I'm the first talk in this session. So I'll just give you an example. VASS consists of states and transitions, the arrows between states. They're labeled with vectors, which makes a lot of sense. Vector addition systems is shortened to VASS. And the question I care about is reachability. So I'd like to know from some initial configuration, so imagine this blue node A with counter values 0, 0, whether I can reach some target node G with counter values 4 and 5. And the important detail is that the counters must remain non-negative at all times. And like, it's not particularly big instance, but I don't know if anyone's solved it yet. I mean, it's very carefully chosen, so it's probably a positive instance, and sure enough it is. If you start here with 0, 0, you can go here to 2, 0, up here to 5, 8, and you continue around, you get here, and you've noticed that if you were to take either path via F to G or just directly to G, you wouldn't reach 4, 5. So you have to kind of cheaply take the cycle back through A and B, and so you do this twice, and now, conveniently, if you go from 9, 25 at D, you can get to G with 4, 5. So this is a positive instance. Reachability is really hard, and in general, you don't need 2 dimensions. You can have any number of counters on this thing. So when I say like a 2-dimensional system, I was talking about the previous one, you can have a 3-dimensional, 4-dimensional, whatever. And yeah, reachability asks from an initial configuration, can you reach a target? I hope that's clear enough now. I'm not studying the full reachability problem. That's been well studied by a lot of people in this room. So instead, I'm going to talk about simple vector addition systems. And the kind that I care about are flat VASS. What is a flat VASS? A flat VASS is a very simple kind of VASS where for each state, there is at most one cycle that contains that state. Here's 2 examples. That one's flat because there's the cycle PQR. There's a cycler S, nothing at T, but no state belongs to 2 cycles, whereas the one on the right is not flat. There's this ABCD cycle, and there is the CDF cycle, so that thing's not flat. Roughly speaking, a flat VASS can be thought of as a directed graph with cycles that are kind of disjoint attached to the vertices. It makes the system very simple. The reachability problem in flat VASS is in NP, regardless of the number of counters and regardless of whether you use binary or unary encoding. So it's not too difficult. And if you have just one counter and binary encoding, the problem is NP hard. Great. So then with any number of counters with binary encoding, this problem is NP complete. But what about unary encoding? In dimensions 1 and 2, even if it's not flat, reachability is in NL, so this is very much within P. And then for dimension 7, it's NP hard. This is improved to 5 and then to 4. So the only question, which must be burning right now, is what is the complexity of reachability in unary flat 3 VASS? I'm sure you're all very curious. These 8 people were indeed. But that's not flat enough for me. So I study linear path schemes. These are a kind of flat VASS where you're not even really allowed branching. You just have a linear path with cycles disjoint connected to the states along the way. Even that's not flat enough. I want a simple linear path scheme. The cycles are only allowed to be self-loops. There's almost no structure in the states and transitions here. It's kind of insane. And it was asked whether there was any constant dimension greater than or equal to 3 for which reachability was in P. Because remember, in dimensions 1 and 2, it's already in NL. So what about for a higher dimension? No. For dimension 3 already, even in simple linear path schemes, the problem is NP hard. And now a technical slide, so you can go to sleep. How do we do it roughly? The idea is to reduce from SAT. We're going to use the Chinese remainder encoding for SAT over K variables. So I'm going to have some natural number that's going to represent an assignment. I'm going to get the first K primes, and the assignment is going to look like, if xi is true, I want to be congruent to 1 mod the ith prime, and if xi is false, I want to be congruent to 0 mod the ith prime. And I'm going to turn my instance of SAT into a massive conjunction of non-divisibility queries. What do I mean? So imagine I have a clause x1 or not x2 or x3. This looks like I want to be equivalent to 1 mod 2 or 0 mod 3 or 1 mod 5, right? 2, 3, and 5 are the first three primes. This is only falsified when n is congruent to 10 mod 2 times 3 times 5. So what you need to check is whether n minus 10 can be divided by 2 times 3 times 5. That's a non-divisibility query. Do this for all of the clauses. And you actually have to do it for checking an assignment. You have to check that you're, like, for example, if you're looking at like x3, right? So you need to be congruent to 0 or 1 mod 5. Here you check that you're not congruent to 2, 3, or 4 mod 5. You get a massive conjunction of non-divisibility queries. And then the next step, which I don't have time, but is the best bit, unfortunately, it's a highlights talk, is you kind of come up with some very funky gadget in a two-dimensional system that has access to zero tests that can test non-divisibility. I promise this is the best part, but I don't have time. And then you simulate these zero tests with a technique that's already been known, and then you get a three-counter system that does the whole thing. And so that's roughly the idea. Unfortunately, like, the two nice ideas here are how to encode SAT and how to do non-divisibility. And encoding SAT motivates non-divisibility, so I had to present that one. That was not as cool as that one. So really, like, I promise you the juice is there. Come and ask me. And to conclude, I'll just give you an idea of the other things that are in our paper. So I just gave you a rough idea of how reachability in unary, three-dimensional, simple, linear path schemes is NP hard and is therefore NP complete. And this closes a nice line of research on the reachability problem in flat VASS. We can then go a bit further. So if you want something even flatter than that, you go to ultra flat, introduced by Jerome. Here, you're not even allowed to change the counter values between cycles. You just have these tiny self loops where you can update the counters. We also show this as NP hard, but we pay for an extra dimension, unfortunately. So we get four-dimensional systems here. And then you go even simpler to unitary systems. And now we're it's just theoretically interesting at this point. It's like, how simple can your VASS be whilst reachability is challenging? I won't bother defining unitary. And somehow, what on earth is an inverse dimension simple linear path scheme? Come and ask me if you're interested. And then after all, this is the tractability border. We do have a polynomial time algorithm in that if you're given a unary two-dimensional simple linear path scheme, but where the initial and target configurations are encoded in binary, so they can be very large values, then the problem is decidable in P. This increments on what was known for two-dimensional systems, all in unary, including the source and target configurations. This algorithm is ridiculously complicated. It was the basis of the joke earlier. This is the reason why we didn't submit to stock and the reason we didn't submit to ICAL. So if you want a really complicated algorithm, come and ask me and I'll have 5 hours of things to talk about. Thank you very much.
Thanks. So we have time for one question, one or two questions. We have 1 minute.
You should take your VASS in Belgium if you want them flat. That was not a question.
Yes?
Not smart. Can you say what ultra flat is again?
So you've got, bear with me. You've got these guys, but the transitions between the states, so the ones on the path itself have to have zero update. So you're only allowed to update on the cycles. We really, in the juice, leverage that you can update between. What we do with an extra counter is basically store a small value that you have to put onto another counter and then shift back. So we pay for this with just one counter. Yeah, that's ultra flat.
Okay, thanks.